Good morning, everyone. I welcome you all to this next lecture of dynamics of machine. And in this lecture, we will continue our discussion over the governors. So, in previous lecture, so far we have discussed about the uh, important terms related to the governor. We saw what was governor axis, the arms of the governor, then spindle of the governor, what is meant by the height of the governor, radius, then lift of governor, and so on. Okay, governor equilibrium, speed, sleeve, and this fly balls, right? And how it works. To saw an animated video in which we saw the working of governor and how the radius and height changes with the change in the load and speed, and with the help of this sleeve, how this throttle valve is controlled. Okay, this we saw with the help animated video, right? We also saw the classification of centrifugal uh, classification of governors, which are broadly classified into two: inertia and centrifugal governors. And centrifugal governor has following types, these types, right? We also saw comparison between flywheel and the governor, how they both are different. A flywheel works for the cyclic fluctuations, and governor works when there is fluctuation due to some external factor, right? Change in load due to uneven reasons. Okay, so this is what we discussed in previous classes. Now in this class, we are going to start with the operation of the governor, that how a governor operates. Okay, so as you can see this diagram, uh, this diagram is basically a line diagram of a governor, and this is the axis, right? This is the axis of rotation, or which goes to the spindle, right? Axis of rotation. Then these are the upper arms. We already know all this, right? These are the balls. Then these are the lower arms, and lower arms are attached to the sleeve. Okay, the mass of the sleeve is denoted by capital M, and the mass of balls are denoted by small m. All right, keep this in mind. Its weight would be mg, and this sleeve's weight would be capital Mg. Okay. The height of the governor and the radius of governor we have already discussed in previous class. All right. Now let's go how this operates. With the rotation of the crankshaft, the spindle S, which is geared to it, also rotates. Right. So when the crankshaft rotates, the spindle also rotates because it is geared to it. As we saw that if they are 90° at 90° to each other, then we will use the bevel gear arrangement. All right. Now let the speed of rotation of spindle be omega. Let's say that this omega and the spindle is rotating with the speed omega, right? It is rotating about its own axis, and its speed is angular speed is omega. Due to rotation, the balls of mass m fly out and exert centrifugal force of magnitude F is equals to m omega square r. Right. So we know that centrifugal force, the expression for centrifugal force is m omega square r. So when these balls rotate, they will exert an outward force. Since spindle is rotating, attached to it, this arms will also rotate about this axis of rotation, and since balls are rotating, they will exert an outward force, which is centrifugal force, and its magnitude would be m omega square r, right? M, small m, is the mass of fly balls, omega is the speed of rotation spindle, and r is the radius. All right. Where r is the radius of the circle of rotation of the center of gravity of masses in meters. So this r, radius of rotation. Okay, this is the value of r, which is to be taken in meters. Okay, please note the units we are using over here. So radius of rotation is to be taken in meters. Small m is the mass of fly balls in kg. Omega is in radians per second. Okay, so when we keep this unit, the force comes out to be in newtons. So when the spindle rotates, along with it, these arms, sleeve, balls also rotate. Because of rotation, these balls exert an outward force, which is centrifugal force, and its value will be F omega square R. So pretty straightforward up to this point. Now, the centrifugal forces due to these masses are balanced by the weight of the sleeve. Since the centrifugal force, it will try to pull the balls outside. Okay, so not here, but a little bit upward. This ball will acquire a new position, something like this. Okay, this arm will come something like this, and this arm, the lower arm, will raise something this. So obviously, since the lower arm has came up to here, so the sleeve also has to lift along with the lower arm. Okay. Sleeve, next position of the sleeve is over here. Now this outward force, m omega, this what this sentence is saying that, that this outward force, the outward force, it is balanced by the weight of the sleeve. Okay, weight of the selecting downward, and this uh, unbalanced force is acting towards outward, and these two forces will balance each other at some point. Okay, again, the centrifugal forces due to the mass, due to these masses, are balanced by the weight of the sleeve. All right, so obviously do not have same line of action, so we will be calculating the moment about any given point in order to write the balancing equation. Okay, how we'll do that, we'll see in the further slides. Now let us assume that there is decrease in load on the engine. So if the load on the engine if suddenly decrease, then what will happen? Okay, so assume that the load on the engine has reduced. The engines will speed up, and as a result of that, the centrifugal force will outbalance the weight of sleeve, sliding it up. So when the load on the engine reduces, what will happen? The speed of the engine will increase all of a sudden. Okay, so what will happen? These balls will start rotating at a higher speed. Why? Because engine is now rotating at higher speed. So the spindle will rotate at higher speed. As a result, this uh, balls will start rotation at higher speed, and because of it, the sleeve will move upwards. Okay, so the radius has increased, the height of rotation, the height of governor has decreased, and the sleeve will move up. Okay, let's read this again. The engine will speed up, and as a result of that, the centrifugal force will outbalance the weight of sleeve, sliding it up. Since the radius of rotation increased, so what will happen? This centrifugal force will lift the sleeve up, because this force value became greater. Why? Because r increased, or and omega increased. Two things are increasing, so the value of this force will increase, which will outbalance this sleeve, weight of sleeve, up to some point. Okay, so as a result, the sleeve has to slide up. All right, this action of the sliding of the sleeve will in turn operate the bell crank lever L. Okay, so in previous diagrams we saw that a lever is attached to this sleeve. So as this moves up, the bell crank lever, which is hinged from this point, it will operate the throttle valve. Okay, so this is what is written over here. This action of sliding of the sleeve will in turn operate the bell crank lever L, which in turn closes the throttle valve and decreases the fuel supply. So as the load increased, let me summarize till here. So what this is saying is the load on the engine decreased. Okay, so due to which the speed of the engine increased all of a sudden. Since the speed of engine increased, the uh, the centrifugal force which is acting on these balls, okay, so the spindle will also start rotating at higher speed. So the balls, the centrifugal force which was acting on the ball will increase. As a result, this will slide the sleeve upwards. Okay, since the sleeve is slided upward, the lever which is attached to uh, the sleeve will be operated, and in turn it will reduce the fuel supply of the to the engine. Okay, now now the net result will be the drop in speed. Since the supply of the fuel has decreased, supply of the fuel to the engine has decreased, the net result will be a drop in speed till the new configuration is achieved, when the centrifugal force is again balanced by the weight of the sleeve. So since the fuel supply has reduced, now the speed of the engine will reduce. Speed of engine is reduced, so this again the the value of the centrifugal force will reduce. Why? Because omega and r will get decreased. Okay, since this value is decreased, so this will result in the drop in speed. Till how far the speed will drop? Till the new configuration is achieved, when the centrifugal force is again balanced by the weight of the sleeve. Okay, uh, centrifugal force, this centrifugal force is again until it is balanced by the weight of the sleeve. So this will start moving little bit downward until the centrifugal force is balanced. Okay, this variation in speed for the two configuration obtained with different loads has to be within prescribed limits. So as we saw in the first lecture, that for best output, the engine has to uh, keep its speed of rotation within certain limits. Okay, so this is what is saying over here, that the variation in speed for the configuration obtained with different loads has to be within prescribed limits. So whatever limit is prescribed by the manufacturer for the engine, the of the these two configurations has to be within those prescribed limits. Okay, so this is what the operation of governor was. This is how a governor operates. Okay, let's move forward. Now we will be starting with each and individual governor. The first governor is the watt governor. Okay, right. It is assumed that the mass of arms, links, sleeves are negligible in comparison with the mass of balls and are therefore neglected in the analysis. So the assumption which is taken is the mass of these balls, okay, the mass of these balls is far more greater than the mass of these arms, okay, the mass of sleeve, okay, and mass of the link, that is the lower arm. Okay, so the speed, the mass of ball is far more greater than the all these added together. All right, so they are negligible and hence they are neglected for the analysis purpose. Okay, all right. So again, this is the similar diagram, and for practical purpose, this arm this arm is not exactly attached to the spindle, because how it will rotate then. So there is another arrangement made, which is mounted on the shaft of the which is mounted on the sleeve, and then these arms are attached to that arrangement. Okay, fine. The height is to be taken by extending these arms up to the spindle. All right, you will not measure the height until here from the plane of rotation. The height has to be measured with this arms extended until it touches the sleeve. Okay, so this will be the height. Now, uh, in order to balance the forces, as their line of action is different, so one of the line of action is this, another force is acting like this, so they both have different line of action, right? So we'll take the moment in order to balance, write the balancing equation. So this is the topmost point is O, this is H, all right, or we'll look over here. This is O, and for ease of drawing, O and H points are coinciding. The balls are situated at point B. This sleeve is attached at point C. All right. R is the radius of rotation and small h is the height. Okay. So taking the moment about point O, where is point O? This is point O. Okay, this is point O. So it says F into H. F into H. Where is F? This is F. This is the line of action of F. And how far is it from the uh, point O? It is at a distance H. Right? It is at a distance of H. So force multiplied by perpendicular distance, F into H. Okay, and this uh, R. What is the value of R? Sorry, mg multiplied by R. So this mg, where is force mg? Mg force is over here. Small m multiplied by g. Mg force is over here. Okay, this is mg. So its line of action is something like this. And what is the distance between point and this line of action? It is radius of rotation, that is small r. So from this we can see that F into H will be equals to mg into r. Okay, so this is the balancing equation. We'll substitute its values. F is m omega square r. So this r and r will get cancelled, and we'll get this m and m also will get cancelled. Okay, so we'll get the height of governor as g by omega square. The height is equals to g by omega square. Now omega is 2 pi n by 60, so h becomes g by 2 pi n divided by 60 whole square. Okay, so we'll substitute the value of pi and g as 9.81, pi as 3. The value of pi, and this comes out to be 91.2 g by n square. Okay, or we can write it as 895 divided by n square. Okay, by substituting the value of g. So these are the expressions for determining the height. Okay, so I hope this is clear to you. One is h is equals to g by omega square. Okay, another one is h is equals to 895 by n square. Okay, so to determine the height of the governor, we'll use these equations in case of watt governor. All right. Okay. Moving forward, I hope this is clear. Moving forward, there is another method. This was the moment method. We'll use the we can also use the instantaneous center method. Now, what is instantaneous center method? You have already studied in your theory of machines, right? So this is a kind of 4-bar mechanism. We'll consider one half, okay, one half of this diagram. That is the, we'll consider this left half, okay. Now, this is this spindle, the axis of the spindle is considered as link number 1, and this upper arm is link number 2. Okay, spindle is link number 1. This lower arm is link number 3, and sleeve is link number 4. Okay, and they form a slider crank mechanism. All right. Now this m r omega square is acting outwards. That is the centrifugal force. Okay, let's consider this angle as theta. This is angle theta. So the instantaneous center for link 1 and 2 will be I12, which will be situated over here. Okay, I12 is over here. All right. I34 is over here. Okay, this is I23. Okay, of link 2 and 3. Now the I14 will go at the infinity. Why? Because this slider is moving along this axis. Okay, this slider is moving along this axis, so it will be over here, and I13 will get over here. Okay, okay. So now we'll take the moment about I13. So in order to determine these distances, let's consider this is angle theta. Okay, this is angle theta. All right. This is the radius of rotation r, and this is the height. All right. Since this is angle theta, and this would be angle beta. All right, this is angle beta. Now I have one force is over here, mr omega square, and another force is this mg force acting on the ball. Since this angle is theta, this angle is theta, so by geometry this angle also be theta. Okay, and this distance, this link number, and this upper arm, what will be its value? This is r, this distance is r, this distance is h, so this tan theta would be r upon h, right? The tan theta would be r upon h. Okay, so we have drawn a perpendicular from this point and joined this center. Okay, we have created this, so this angle would be theta, and this distance is taken as c, this distance is taken as b, and this height is a. All right, so tan theta would also be equals to c upon a. Okay, now taking moment about I13. Where is I13? I13 is at this point. Okay, we'll take moment about this. So m omega square r multiplied by a. So where is distance a? This is distance a. So this is the line of action of m r omega square, and its perpendicular distance from the center of rotation, that is I13, is a. Okay, and it will be equals to mg, the force mg multiplied by c. So this is the line of action of mg force. This is line of action of mg force, and perpendicular distance from this mg force to center of rotation is nothing but c. All right, therefore mg multiplied by c. So we will again simplify it, substitute the values, and it comes out to be h is equals to g by omega square as we derived in the previous slide. And also if we take the put the value of omega in terms of n, so we'll get version n1 upon n2 is equals to under root h2 upon h1. So the height of the governor is inversely proportional to its speed. So more the height, less will be the speed of the governor, and vice versa. Okay, so I hope this is clear to you. Now let's move forward. So let's solve an example. Calculate the vertical height of the governor when it rotates at 60 rpm. Okay, when it rotates at 60 rpm. So value of n is given to us. Also find the change in vertical height when its speed is increased by 61 rpm. So we have to determine the height when its speed is increased by 1 rpm. Okay, so n1 is 60, n2 is 61. Initial height can be calculated by h is equals to 895 by n1 square. Okay, so h1 comes out to be 0.248 meter. All right, so pretty straightforward question. We can directly use this expression that height is equals to 895 upon n square if the value of n is given to us. Okay, also if something else is given, we can go by h is equals to g upon omega square. So remember these equations. Now change in vertical. When the speed increase from 60 to 61, what will happen? Since we already saw over here that speed is inversely proportional to the height of governor. So if the speed is increasing, the height will reduce. Okay. So we can directly use this equation. H is equals to 895 divided by n square. So H2 comes out to be 0.24 meter. 0.24 meter. This is H2. And what was the previous height? Previous height H1 corresponding to 60 rpm was 0.248 meter. And corresponding to 61 rpm, sorry, this was against the 60 rpm, right? Corresponding to 61 rpm, the height is 0.24 meter. So what is the difference? It will be h1 minus h2, and it comes out to be 0.008 meters or 8 millimeters. Okay, so very simple question. Let's look at another question. All right. A simple watt governor is shown below. Find out the speed of rotation and also estimate percentage change in speed for rise in level of balls by 3 centimeter. So the change in height is given to us. That is h1 minus h2 is given to us as 3 centimeters. Find out the speed of rotation and also estimate percentage change in speed. So this diagram is given to us. This diagram is given to us that initially when the speed was lower, this angle was making 30 degree. Okay, and the length of arm is given to us as 32 centimeters. Okay, and when the speed, this height is increased. Okay, there is a lift in the sleeve. So the height is reduced. There is a lift in sleeve. Height is reduced. So the speed might have decreased. Sorry, height is reduced, so speed has increased. So this lift is given of 3 centimeter. So this is given to us in the question, right? So we can directly use this, that cos 30 will be h2 divided by the 32, right? This is a triangle. This is the triangle, and this angle, one angle and one side is given to us, so we can determine the other sides also, right? So this is the height. This was the height, This height we have named as h2. Okay, this height is h2. So cos 30 would be h2 divided by 32. So h2 comes out to be 27.71 centimeter. Okay. Also, h2 is equals to g upon omega square. This h2 is g upon omega 2 square. So value of g is 9.81. So omega 2 comes out to be 5.949 radians per second. Okay, this comes out to be 5.949 radians per second. So since omega is this much, so n2 will come out to be 56.818 rpm. So when the speed, the speed of engine was 56.818 rpm, the height was, this height was h2, which was 27.71 centimeters. Now, what is the new height? New height is reduced by 3 centimeter. So h1 would be 27.71 minus 3 centimeter, that is h2 minus 3 centimeter. This is the new height, which comes out to be 24.71 centimeter. Okay, so this was the configuration. This h2 was the total height. Okay, and h1 is the new height. So we can use this relation directly, that n1 upon n2 is equals to under root h2 upon h1. Okay, so n1 comes out to be 60.15 rpm, right? And percentage change would be initial minus final divided by the final. So it comes out to be 5.89 percentage. So this is how we are going to approach the questions in case of governor, that most probably the height of governor is asked, or the corresponding speed would be asked, and if not, then some geometrical relations would be given to us. From its help, we have to determine the things which are asked in the question. So I hope this is clear to you. You can also use this, take the screenshot of this and try to solve this question. Okay, so I'll conclude my class over here. Thank you, everyone.